conic sections. We're embarking on the journey through conics. This is a little bit of a challenge. There's a lot of information that we get to look at, a lot of equations we're going to have to become familiar with, and the different components of the equation, what they refer to. So hang on, it's a bumpy ride. So what are conics? These are the curves that are created when we intersect cones with a plane. And conics have different equations, and they can be written in kind of an expanded form. They can be written in what we call a standard form too. And generically, this equation here would be an equation that represents different types of conic sections. Not all equations are going to have all those components in it, but something with x squareds and y squareds, and x's and y's and a constant. We can end up deriving this equation from a given problem. Sometimes we're going to take this equation and have to do a little completing the square, find some other components, and we'll worry about that when we get there. All right, so we take these planes and we slice through our cones and we create these shapes. Our circle, we took a look at circles back in chapter 3. That would be intersecting a cone perpendicular to its axis. And there's the axis of a cone, vertical. We create the circle. If we tilted that plane and intersected, we create an ellipse. If we tilted the plane in such a way where we intersected the cone but ran out through the bottom of the cone, we would create a parabola. And then take our plane and go through both of these cones, and we would create a hyperbola. So this is what conic sections are, and how we would physically derive them from slicing through some cones here. Some other interesting points of conic sections. So what if our plane simply goes through this point of intersection between these two cones? Well, we would have just a common point. What if our plane is along the edge of these cones? We have a line. And if we had our plane going through the edges of the cones, could be perpendicular, could be parallel to the vertical axis, could be the slant like this, but on the outside of the cone's edges, we have this double line creating text. That's just some FYI. We're not going to really work with those. We're primarily going to be working with these ellipse, circle, parabola, hyperbola. In chapter 12, we're going to focus on these three because we've already seen the ellipse in a previous chapter, or we've already seen circle in a previous chapter. All right, here's some websites you can check out. Some of them have some animated diagrams to show you what's going on. Other useful definitions. So how are these crane cones that we see up in those previous examples created? Well, we have this vertical line called an axis line, and we take an axis line and create another line going and intersecting that line at some angle. Then we spin that slanted red line around and we create this shape over to the right. And these are called napes. We have an upper nape and we have a lower nape, and right in the middle where they meet is what we would refer to as the vertex. So those are the shapes that are helping us create some of our conic sections. All right, parabola. First one we're going to look at. Definition: the set of all points in a plane equidistant from a point P and a fixed line y equal negative P. All right, some definitions now. We've got some focus is the fixed point P. So here we have our focus right there. And that focus, by the way, for our parabolas will always be, you consider the parabola wrapping itself around the focus. That will always be the case, whether our focus or whether our parabola faces up or down or right or left. Our focus will always be wrapped up by the parabola. Directrix. Directrix is a line, actually, and it will be equidistant from the vertex. So when I say that, this is an important concept to understand. This distance here between our focus and the vertex will be the same distance that we have between our vertex and our directrix. Those are equidistant. All right, let's keep that one in mind. So the directrix then is this. In this case, it's a horizontal line. But it is a line. It's an equation of a line. Depending on the shape of our parabola, will be horizontal or vertical. The axis is this vertical line in this case that goes and splits our parabola in two equal parts. So it's our symmetry. It's called axis of symmetry, line of symmetry. The vertex, and this is what we just talked about, that equidistant portion. The vertex lies halfway between the directrix and the focus. And again, that's something to keep in mind when we're thinking about equations for this. All right, we're going to show you, I'm going to show you the equations of the parabolas that we're going to consider, and then we're going to take a look at how we get them. So this is our first of our four equations. We have two of them where the parabola is going to be symmetrical around the x-axis. It means it opens to the left or to the right. And then we will have two of them where the parabola is symmetrical around the y-axis, where it opens up or down. In this example, you'll notice the purple parabola opening to the left. And again, like I said, the focus is always surrounded or wrapped up by the parabola. So there's our focus. This line out here that we see is our directrix. We'll say D for directrix. And it's always, again, equidistant from the vertex. And so this distance from the focus to the vertex and from the vertex to the directrix are going to be the same thing. And in this example, where our parabolas are going to have a vertex at the 0, 0, or the origin, we use A to represent that distance. So here we see in our equation of our focus, we're going, here's our A distance, but it's to the left. And that's what gets us to that point there. So the coordinate of this focus point, in this case, would be negative A, 0. Because our parabola opens to the left, our A will be negative. Our directrix is always the opposite of that. So if that point is negative A, that means this equation for the directrix is going to be x equal positive. All right. So going through, you'll notice the equations for left and right parabolas, they do look the same. They both are y squared equal 4ax. Y squared equal 4ax. Again, this is the main difference, what your A is doing. If my A is negative, I'm going to open left, and if my A is positive, I'm opening right. And every time I do something different with these A values, whether open left or open right, you'll notice that it's going to change something. In this case, it's changing both our directrix equation and the focus. Because when our parabola opens to the right, that means our focus is to the right of the parabola, being wrapped up by it. That's a positive value relative to the origin. And then we take a look at our ups and downs. These are the two that we're probably most familiar with. We saw this in quadratics chapter. So x squared equals 4ay. When a is negative, that means it's opening down, and when a is positive, I'm opening up. And again, paying attention to a couple things. When my graphs are going around the y-axis, that means so we're going to pay attention to the value of the focus. We're wrapping around the y-axis, and that means you'll notice our equation is no longer a comma 0, it's now 0 comma negative a because we're opening down. So pay attention to directrix and focus when your axis of symmetry is different. X-axis of symmetry versus y-axis of symmetry. And then here's the difference when we open up. All right, so there are our four equations for our parabolas. Now let's see, where do they come from? How did we get them? That's what this is all about. So we're going to consider, in our diagram here, make this a little bigger. We're going to assign some importance to this. So our focus, in this example, we will use 0, 0a, somewhere located on the curve of the parabola. And then we've got a point down here where our directrix is being intersected by this line dropping from the point, and we will assign that a coordinate of some value of x. Now, we are a y distance away of negative a. So again, paying attention to this. That's negative a right there, that distance, and this is positive a, that distance. So that's why we're going to assign the coordinate of this point as 0, negative a. All right, let's use this and see if, now we have those coordinates of those points, let's see if we can use this to come up with where do those equations that we had come from on the previous page. By definition, these d1, d2 values, distances from focus to a point on the graph, or distance from directrix to that same point on the graph, they're going to have to be the same. So if we set up our equations and we establish that distance 1 is equal to distance 2, let's go find what each of these are. Let's go take a look at distance 1. We're just using distance formula here. All right, we're going to say x value is x minus 0 squared plus the difference in y, so y minus a squared. And we get x squared plus y squared minus 2ay plus a squared. So there's my distance formula for d1. d2. Distance formula now between the point and our directrix. So we have x minus x quantity squared and y minus a negative a, which means it's going to become a plus a squared. X minus x, we get those to cancel. So we just have here a y squared plus a 2ay plus an a squared. All right, so we set these equal to one another, and then let's see what happens. So we have the square root of x squared plus y squared minus 2ay plus a squared is equal to the square root of y squared plus 2ay plus a squared. Now, we can undo both of these roots. We're going to square them. And then I get x squared plus y squared minus 2ay plus a squared is equal to y squared plus 2ay plus a squared. All right. Now we're going to move some things around here. Let's see. Well, my y squareds are going to cancel each other out. It looks as though my a squareds will cancel each other out. And let's go ahead and solve for x squared. So I get x squared equal to, I got to take my negative 2ay and add it to the other side, and I get 4ay. And there's one of our equations that we looked at in the previous slide, and that would be our vertical opening up graph or opening down graph, depending on the value of a. So that is using the distance formula and our definition of a parabola to come up with an equation for a parabola. And we're going to be doing this throughout some of the problems on the homework. So this whole process of developing this distance equal to a distance is critical. And my recommendation is to always set it up in this way, such that you arbitrarily have some point on your curve, call it xy, and your distance 1 will always be, it doesn't have to be in this order, but distance 1 will always be relative to focus and point on curve. And your distance 2 will be relative to point on curve and your directrix. So you don't have to physically see the drawing to be able to do this. Just understand that those are the two distances I will be always comparing. The only thing you have to remember is your focus will already have a coordinate, probably. Your point on your curve will probably be an arbitrary point, xy, unless we give you an xy, and then maybe you're looking for the focus. The directrix, you're just going to have to remember that that's going to have to be given some coordinate value. Now, that will depend on, as in this case, our directrix was the opposite of A, and so we said in the y direction, we knew that the directrix was going to have the opposite value as the focus point. So the focus y value was A, that means the directrix y value will be negative A. And then it'll just be an arbitrary x for this case, because we really don't know where that is. When I say where that is, I'm referring to that point right there. We just knew that it was going to be equal to an x minus A. All right, let's keep pressing on. So now we know where they come from. Let's, a little technical difficulty here. There we go. All right, let's graph some of these and then find the focus and the directrix. So our first one, x squared equals 12y. What you might want to do is remember, based off the formula, what axis I'm wrapping around. And so what I do is kind of just contrary to what you think. When I see an x squared equals something y parabola graph, I know that the x squared means that our graph is opening up or down. So I just know x squareds mean up or down. Y squareds mean right or left. So if that's the case, if my graph is opening up or down, that means my axis symmetry, we'll call axis of symmetry our AOS. Our axis of symmetry is going to be the y-axis. All right. So graphing the following. Well, it's in the form of x squared equal 4ay. That's what we're in right now. X squared equals 12y. So from here, I'm able to figure out that 4a is equal to 12, and therefore a is equal to 3. All right. So we have a situation where my a is equal to 3. All of these graphs right now are going to be graphed with a vertex at 0, 0, by the way. So we're going to have our vertex hanging out at 0, 0. So there's my 0, 0 point. And then now we found this a value. So my graph is opening up. My a happens to be positive. So that means that my focus has a coordinate of 0, 3. And as soon as I find my focus, I am able to then find my directrix, because that will be an equation that will have the opposite a value. In this case, y equals negative 3. And so I can put these points on here. I have my y equal negative 3 line going right there as my directrix. And I have graphed, or I haven't graphed yet, but here's my focus at 0, 3. There we go. All right, there's my focus at 0, 3. And my directrix at y equal negative 3. So what does my parabola look like? You got to go through that red dot there in the center. It's going to open up, but what about width? How do we come up with that? Well, we can use a t-table. And in the case of an x squared equals something y, whatever is being squared is probably what I would plug in for values. Meaning if x squared is shown up here, I'm going to plug values for x and I'm going to find y. Whereas if it was y squared equals something, I'm going to plug values in for y and solve for x. All right, let's put some numbers in here. Let's put a negative 2 in there. Why not put a negative 1? We already know 0, 0 is going to give me 0, 0. So let's just try these points. If I put a negative 2 in for x, and I square it, I get a 4. And then I take 4 divided by 12, I get 1/3, or 0.33. Well, negative 1 in there, I get a 1. 1 divided by 12 is 1/12. And then 1/12 again, and 1/3. Those aren't some huge numbers, so maybe I'd want to, just for the sake of having something that's not going to be decimal, maybe I just test. I'm going to just add these in here. What about a negative 4? 16. 16 divided by 12 is 4/3. And 4/3. So I have a couple points here. Negative 4 and 4/3, just 1 1/3. And then negative 2 and 1/3. And then we have symmetry on the other side of that. So those points there would define my parabola. And let's see what we get. There it is. All right, so we located our focus. And again, I'm going to need you to, if I ask you to do that, or if I want you to graph these things, I want you to give these as part of your graph. So there's your focus, and there's your directrix. All right, what about this guy? We have a y-squared now. And what did we say? We said x squared, my graph is going up and down. This means my graph is going left and right. Okay, my graph is going left and right, and it's taking on the form of y squared equals 4a to the x. I can see here that 4a is equivalent to negative 16. And so then a is therefore negative 4. So this means that my focus is going to have an equation of negative 4, 0. My graph is opening left. My directrix then, because it's the opposite for a situation where I'm centered at, or where I have a vertex at the origin, would be 4. Now, because my graph is opening right or left, that means my equation has to be x equal 4. So there's my focus and my directrix. And we'll go ahead and locate them on here. There's my focus. And x equal 4. There's my line, x equal 4 for my directrix. And we would then begin to take a look at some points here. I'd plug some t-table points in, and we would discover, just for the sake of time here, we would discover that wrong one. There we go. There's my parabola, and there's my vertex. Forgot to mark that. Vertex 0, 0. So, opening to the left. What about finding equations of parabolas? Given some information. So, right now our vertex is still at the origin. All right. So we have our vertex 0, 0. Our axis is the y-axis. All right. So our axis of symmetry is the y. And we have this point on the graph. Somewhere on the graph. That's not given to us as a focus or a directrix, which wouldn't be a directrix because it's not a line, it's not an equation. But it's just some point on my graph that we're supposed to write our equation. Okay, what do? We have to first decide what form does this equation take. Well, if I'm going to be symmetrical around the y-axis, it's going to be of the form x squared equals 4ay. And in order for us to write equations in this standard form, we call it, really what we need to find is a. So if we have to find a, that would be nice to be able to plug something in for x and y. That is what this is for. That is a coordinate. So I have x, I have y. Plug those in, and we get negative 6 squared is equal to 4a times negative 3. 36 is equal to negative 12a. Therefore, a is negative 3. And we can finally write our equation that x squared would equal 4 times negative 3y, or x about finding the coordinates of this graph's directrix, or coordinates of the focus, and then the equation of its directrix. Again, it's has a vertex at 0, 0, so it makes this a little easier. Once I find that A value, I can use that to help me come up with this next part here. So we have a graph that's opening, in this case, down. And how do I know that? The focus is related to this A value, and if my focus is negative 3, that means my coordinate of my focus is going to be 0, negative 3. And then, once we know our focus, we know that we can find our directrix. This graph opens up and down, means I have a directrix. It's a horizontal line. And in this case, my directrix will be the opposite of my A value, or in this case, y equals 3. All right. Okay, this is one just for you to try. If you want to give this one a go, and then might want to pause the YouTube video right now, and I will work through it, and you can see how you did. So the axis of symmetry is now our x, and we set this thing up where I have now y squared equals 4ax. And once again, we have y given to us. We plug that into our equation. We have x given to us, and we have 64 is equal to 16a. A would equal 4. So now my graph is opening right. I use the a and fill it into my equation. X squared equals 4 times a y, and I get that x squared is equal to 16y. What is my focus? Well, relative to the a, if my a is equal to a 4, my focus will be the opposite of that. And because my graph is opening left and right, first of all here, put the coordinate in, and then it might help you to see whether I have to use an x equal line or a y equal line. So my focus is on the x in terms of a coordinate, so that means my directrix will be the opposite of that as an x equal equation. So there's my directrix. All right, very good. What happens when our focus is somewhere else that's not on either the x-axis or the y-axis? So here, this is a situation we're going to get to in section 4 where we talk about a translation, but we're going to kind of peek at it and think about this answer through the use of our distance formula. We've got a focus that's at negative 3, 2, and a directrix that's at y equal negative 2. So maybe let's get a little visual here of what has happened. All right, negative 3, 2. There's my focus. Y equal negative 2. There's my directrix. Now, simply from that, I should be able to figure out where my graph is going. If my directrix is a horizontal line, my graph has to open either up or down. And now because my focus is above the directrix, I know that my graph is going to open up. Now there's other things that we know as well. Basically, we go back to our definition of a parabola. And one of the things we talked about was that the vertex of a parabola will always be halfway between your directrix and your focus. And so in this case, if my directrix is a negative 2 and my focus is at a positive 2, halfway between there would be putting my vertex right there. So I can tell from this that my graph is going to open up. But let's use the equation and see how we can come up with this. Again, we're going to be thinking about distance formula here. And we talked about it in that last example. So distance 1 refers to our focus distance to a point on my graph. And distance 2 will be directrix written as some coordinate here. I'll just arbitrarily assign some coordinate x, y, to, now that might be confusing. Directrix to a point, the same point that we have up above. All right, let's go ahead and find our D1. Again, don't need to draw this out. We're going to take x minus, we're going to our focus now. So x minus a negative 3 makes us an x plus 3 squared. Y, arbitrary point value, minus 2, the y value of my focus. X squared plus 6x plus 9, plus y squared minus 4y plus 4. And all of this is under the square root. We're going to eventually square it both sides anyway, so I'm just going to leave it like that. D2 then, from our directrix. Now our directrix, again, coordinate-wise, what we have is we know that this point has the same value of opposite of our focus value there too. And we know it's actually going to be negative 3. But I'm going to write this. And then we're comparing that again to some arbitrary point x, y that's on our curve somewhere. Just a second. Oops. So we know that my directrix is at the y value of negative 2. The x value, depending on the way I drew my line from my arbitrary point to my directrix, it might not be directly below my vertex. So if I had drawn my parabola, let's say it looked like that, and I arbitrarily assigned some point x, y, let's assign this as my x, y point, then directly below that I will know that I have some x value, in this case negative 2 is what I will use for my directrix. So I shouldn't have put the point directly under the vertex. We have to move it off to the side over here. All right, so then we go and we find this distance. This is the distance from my directrix to x, y. So if I have my x value differences squared, and then my y, in this case I'm going to have plus 2 squared. Then we get, the x's cancel, and I end up with, again, y squared plus 4y plus 4. And again, I'm ignoring the square root because we're going to have to square both sides anyway. All right, we then set, we know that since d1 is equal to d2, we can set x squared plus 6x plus 9 plus y squared minus 4y plus 4 is equal to y squared plus 4y plus 4. All right. So what happens? Y squares cancel. It looks like at least these 4's will cancel. And I end up with x squared plus 6x. We're going to have to subtract this over to the other side. Minus 8y plus 9 would equal 0. And that would be my equation that I have for parabola given the focus of negative 3, 2 with a directrix of y equal negative 2. Sometimes, instead of showing the equation like this as an equal to 0, we might solve for y. And how do I know I'm solving for y? It's because this parabola opens up. So if I did that, I'd have that x squared plus 6x plus 9 is equal to 8y. And if I divided everything by 8, I'd have y is equal to x squared over 8 plus 3/4 x plus 9/8. And then we have our parabola form that we're most used to probably seeing, and that's our standard ax squared bx plus c form. But either way, I think either way would be fine if you wrote it in terms of y or just left it in terms of the 0. It would be good. All right. So that's using our distance formula to come up with our equation, given some arbitrary points there. It might be helpful if I drew the d's in. Now that's d1 right there, and then this was our d2 value. So where do we see these parabolic shapes in the real world? Well, suspension bridges, arch bridges, where else am I? And recording microphones actually use parabolic shapes. Anyway, let's take an application related to recording and see if we can use a parabola to come up with this thing here. So you've been watching NFL, and you know you sometimes see those guys on the sidelines with those funny looking, they look like your satellite dish on your house. But what they are is they're a microphone. And they're a paraboloid, which is the shape that you would get if you took a parabola and you spun it around its axis. You create a three-dimensional figure called a paraboloid. And these paraboloids have this microphone located somewhere on this axis of this thing. And they use this to record the sounds of the game. So we have a situation where we've got a 3-foot width on this paraboloid. It has a depth of 1 foot. And we want to know where should we put the microphone so that we optimize the sound recording. All right, so here I have a little XY table that we can use to create our 2-dimensional drawing of our parabola. And then see if we can use that information to figure out the answer to this, where should I put the recording device to optimize our sound. Well, that sounds like, or maybe it doesn't sound like to you yet, but we're talking about the focus. So what's happening here, the sound, so there's the shape of our microphone. You got these sound waves coming in, and they hit the parabola, and then they bounce. And if we put the focus, the microphone at this focus point, we're concentrating all of that sound that's coming in, being deflected off the shape of the parabola into that particular point, and that's going to optimize our recording. So that's what we want to find, is we want to find the focus. All right, let's draw this thing. We know it's 3 feet across. We're going to use the y-axis as our center axis. That's our axis of symmetry. And it is 1 foot in depth. So we're going to center it with a vertex at 0, 0. 3 feet across means we're going to go left 1.5 feet and right 1.5 feet. And it has a depth of 1. So left 1.5 up 1 would be the outer left edge of this parabola shape. Right 1.5 up 1 would be the outer right edge of this shape. And we know we have something that's looking like this. So there's this microphone. And we're trying to find where is this focus. It's going to be somewhere above that vertex. My parabola is opening up. All right. Well, let's go and see if we can find this thing. So our equation, we know generically, is going to be x squared is equal to 4ay. And I need to find a. Because A will help me find where my focus is. And in this particular parabola, my focus is going to be 0, A. So that's what we need. Well, I have some points that I can use. I have point 1, point A. So let's just say we're going to use 1.5 and 1. So if I did 1.5, I squared it, equals 4A times 1. I have 2.25 is equal to 4A. And if I divide 2.25 by 4, I think, if I'm not mistaken, we get this. Now this is in feet. This is in feet. And we don't want feet. We want to work with inches because the guys who are going to be manufacturing this thing are probably going to be dealing with the inches. All right, so let's convert this into inches. Conversion factor, 12 inches per 1 foot. Units cancel, and I think it's 6.75 inches. Is what A is. So focus-wise, I'm at 0, 6.7, 6.75 inches. So there's 6 inches, or a little bit above that. So right there, at 6.75 inches would be the ideal place to put this microphone so that I optimize the recording level. So that's an application we have. All right, there's 12.1.